Lucky you, it's the race. And we will start your timer for 30 seconds in 5 seconds. Make sure you identify all the information you possibly can. Five seconds. Bing. Okay, what do we got? So, first and foremost, what do we have? We have some IR spectroscopy. Oh my goodness. Let's try that again. This is IR spectroscopy. We take a look. Those show up just under 3,000, which means these are all CHSP3s. Don't get bogged down in the number of signals within that. That's not a big deal. The other thing that can be difficult is knowing exactly where that 3,000 line is. Get a piece of paper and hold that paper up to your computer screen, because it'll be an online exam, and align the bottom of the paper with the axis down here. That can help you to define where that 3,000 line is, because if it's just a hair over that line, then we'd be looking at CHSP2, right? But it's not. CHSP3. We go through and look at the rest of this. Here's our 1500. I would do the same thing. That's under 1500. I'd ignore it. Which means in this spectra, all I get is CHSP3. Dang, that was boring, wasn't it? You didn't need 30 seconds for that. Let's see how you do with the next one. Starting now. Five seconds-ish. And hopefully you can immediately jump on this and say that we are looking at mass. Nope, not mass spec. Just because it's not the next one after IR doesn't make it mass spec. This is actually carbon NMR. So it is misleading because the peak's there, but if we can see as our tip-offs, we're looking at ppm, so this is going to be NMR. Our value up at 200 means that this is going to be a carbon NMR. For our analysis, I see 1, 2, 3, 4 peaks, which means 4 unique carbons. The next part would be their chemical shifts. If I remember correctly, I think it's that 50 line. Oof, I should go back and review that. Sub 50, we're looking at our alkanes. And I believe we need to be at least 100 on to be looking at our alkenes or aromatics, so our double bonds, which means that last one is who knows? I don't. And that's it. Okay. Which then means we move on to our next spectra of, for you to tell me. 30 seconds again. I think we're there. Let's call that 30 seconds. So hopefully I'll figure out that finger magic trick in a second. Doubtful. We're now looking at mass spec, a couple of the big tip-offs, M to Z. That's our mass to charge ratio. Remember that our charge is typically coming in a +1, which means what we can do is look at this as just a mass value. Going through and looking at our spectra, I'm going to throw out that this is our tallest peak, furthest to the right, which comes in exactly at 110. So this would be our M+, that would be our grams per mole for the compound. It is even, which means no nitrogen. If I look for an M+2, that would be 112. There is a tiny little peak there, but it needs to be in a 3-to-1 ratio, which it is not, so no bromine. Whoops, that would be 3-to-1 is no chlorine. A 1-to-1 ratio, which it is not, which would mean no bromine. It is less than 127, so iodine is not on the table, so we're likely not iodine either. Right? Those would be our big conclusions. I would hope I could nail down some information out of the multiple choice. If not, I'm probably being asked for a possible formula. To go to that possible formula, the only information I've got is 110. No nitrogen, no evidence of nitrogen, no chlorine, bromine, or iodine. So that means we're likely looking at 12 carbons, or not 12 carbons, a mass of 12. I'm bad at my times 12 tables, which is a bit irritating, but you can't hear all that clickety-clacking in the background where I'm pulling out a calculator and determining that there would be 9, and 9 times 12 would be 108. I knew that. It would be a remainder of 2. This would suggest I could have 9 carbons and 2 hydrogens. That hydrogen count is really, really low. So what I'm going to do is subtract 1 carbon and go with a C8, and then I'm going to have to add that mass of carbon to our hydrogens, and I'm going to get H14. Right away, that's probably what I'm going to key in on a multiple choice, because that looks like a decent balance to me. What does that looks like coming from? CnH2n plus 2. Okay? That is a fully saturated, so all single bonds and carbon to hydrogens. So that ratio looks about right. But I could go ahead and check it, go C7H, now 14 plus that 12 would be 26. Pretty sure that's too high, but just in case, if it was C7H, 2 times 7 is 14 plus 2, fully saturated would be C7H16. That means I went way too far. That formula doesn't actually make sense. And I would have 2 potential formulas that I could work from. If I had, say, some more information, like maybe in my IR tells me that I have a carbonyl, that means oxygen is present, and I could adjust my formula by subtracting out the oxygen. I don't have that information, which means put 30 seconds back on the timer for our hardest spectra. Go. Finger magic is clearly not my game, so let's go ahead and take a look at what we see. First and foremost, okay, this is where I would recommend you actually had the table set up. We could look at our number of signals, okay, and in this case we get 3, which means 3 unique sets of hydrogen. 1, and we'll color code them. 1, 2, 3 as our unique sets. If we wanted to go through and look at our chemical shifts, the red one comes in about 2.1. If you remember from one of our past slides, we talked about that. A 1.5, and our purple at 0.9. Right? The 2.1, depending on your kind of perception, so this would be our interpret. Hydrogen to carbon, probably likely, but it could potentially be a little bit thin on evidence for that at this point. So you might put that as a question mark. The 1.5 is definitely within that range. I would say a solid guess there is calling that as a hydrogen to carbon, and the same for the purple one. We would then move to, ooh, shoot, kids are coming home. Our integration is the next thing out of this. This becomes tricky on looking at these peak intensities. I'm going to guess that that purple one, I really just want to say that's 3, but that could come in as 6. Ideally, this would be given to you. That blue one, because it's wider, I think is the same as the red one. I think are both going to come in as 2s. Okay, what does that mean for our interpretation? Interpret H hanging 2 bonds. Note that now I will go in and show those 2 hanging bonds. We'll do the same thing for the blue one because it had a 2, and then the purple one, we get 3 hydrogens with 1 hanger. We look at the multiplicity. This is now the number of signals we see. In the multiplicity, we go through and count that out. The red one has 3 peaks. The blue one has 1, 2, 3, 4, 5, 6 peaks. The purple one has 1, 2, 3 peaks. When it comes to neighbors, and so this is why it's nice, is now that we've got that information down, I actually don't need to look at that signal anymore. We look at our neighbors, the red one, we said n plus 1 equals the number of peaks. So 3 neighbors, 2, 5, 3 comes in at 2. Yep. So what does that mean for us? Well, that means that top one with our CH2 has 2 neighbors. The easiest way for that to come out would be next to a CH2. I don't know what that CH2 is connected to, so I'm not going to go that direction. The next one we said was a CH2. To have 5 neighbors, the easiest way to do that would be to split that as a CH2 and a CH3. The last one, that was a CH3 with 2 neighbors, the easiest way to break that would be a CH2. Right? Because I don't have any other information, I'm not going to venture a guess on how I could put this together. Okay? If we were in that boat and you were really trying to force hands, we could try and play around with it and see what we came up with. Right? So for instance, this could potentially be the purple, which would make this one the blue, which would make this one the red. So if we were to assemble that all together, we could foresee a structure along these lines. And then that red one. Problem is, I get that hanging spot. Okay? And what connects there? Since I don't have any other evidence, there could be all sorts of things that could connect in on that spot. That's where I would have to rely on other spectra, or if it was a multiple choice, the answer choices themselves to help me whittle that down. Okay? With this case, because it's 2.1, I'm actually going to bet that if I looked at my carbon or my IR, I would see evidence of a carbonyl. That's going to throw another bond out there, and what I would do is actually duplicate out the other side. Okay? That's just me guessing based off of patterns and my experience. If you don't have that experience, it becomes a little bit harder to do. That's why you should do some more practice. Okay? With that, that was the last spectra in this list and our last slide. So thanks for watching. Hopefully you're struggling through and you've got questions for me. And with that, have a good night or day or weekend wherever you may be.